YouTube. Welcome to my lab report 6, where we worked on magnetic molasses and we did our own demonstration of using an aluminum tube. And let's put out the purpose materials. So, of course, it shows how changing a magnetic field induces a circulating energy field and current. And what we did is just use a classic demonstration that YouTube uses by using a conducive non-ferrous tube, and it just shows how a magnet may just go through that tube and be slowed by electromagnetic induction. So the materials we used was a smartphone, a roll of aluminum foil, a magnet, and also a meter stick and ruler for measuring dimensions. So for the equation and models, even though it's kind of scattered, I can explain it to you. This is the magnetic field of a tube or a dipole itself. And this would be the magnetic field of a long wire. So this is just EMF, this is Faraday's law. You have your position and velocity equations, but also we're going against the force of gravity because it's slowing down but it's still being pressed down by Earth's gravity. Well, yeah. So the assumptions that we have is right here. We're just going to treat it as an ideal magnetic dipole. The aluminum tube is assumed to have uniform conductivity and thickness. The magnet will fall down straight down the center without any form of trouble. There's no air resistance, considering that we're not going to find it, and it's considered negligible. The magnetic field strength should remain constant and stay ideal. And also, external magnetic fields, like the Earth's field, is supposed to be assumed to have stayed insignificant. So here's our initial conditions and results on what we got. So it stayed relatively for 1.49 seconds. And here's the initial conditions that we had for the tube, as well as what could be the default fall time without the tube. So with the mass of the magnet, we recorded as 0.25 kilograms on the scale. So unfortunately, I couldn't get real footage of it, but we're going to be using this for our computational. So as you can see, here's our computational. You might want to pause this, considering that I'm currently almost out of time. Here's our step 3, which seems to be correct. Here's our step 7 through step 8, which should be good enough as well. And coming through here, we have our graph and also what it's supposed to look like once it reaches the bottom of the tube. So the coating is supposed to have this blue light represent the magnet falling down the tube, and then it should be relatively slowing down. So as you can see, as it was falling down, it started gaining a lot of acceleration. It had an acceleration, so thus its velocity was going up. But as soon as it got down the tube a little bit more, it started going up and started slowing down, in which it stayed at that relative velocity per second all until it fully dropped. And it took us 1.482 seconds for that, meaning that the computational and the actual experiment is the same. So, of course, our results and what is that there's a close agreement between the computational model and the experimental observations, but the computational model just gets rid of the small discrepancies that may happen from real-world imperfections, such as an aluminum tube just having a different model, and the model is just a perfectly uniform conductor. So for our results and what if the resistivity was reduced as close as possible to 0? I would say that the conductor's resistivity was just going to be reduced to 0. And any EMF induced would just have no form of good currents or eddy currents, which is basically researched. If I could have my notes, but I'll leave that there. But of course, there's also Lenz's law that can help out, in which case it says the currents generate a magnetic field that opposes the change in flux that's created by them. And then what if the holes or slots that were cut into the tube, if holes or axial slots were cut into the tube, the continuous circular paths would just have to be broken, meaning that the induced ring circuits will just be a little bit weak, will be actually much more weaker, and forced into shorter fragmented loops. And there would be more higher resistance, and thus that would make the magnet fall faster. That concludes my entire lab report. I hope you've enjoyed, and thank you for watching.